Hello and welcome to everyone joining us for the live stream, both on LinkedIn and YouTube. This is our Next Generation AI series. I'm Beth Carey, the CEO and co-founder of Pat Inc. And welcome also to those who are watching this as a recording. Today's session it's not about scale because it's not in the data. And we're joined by Dr. Walid Saba to discuss this topic with John Ball. They'll also cover why large language models can't get to real understanding. First, a bit about Walid. Walid is a PhD in computer science from Carleton University and a recognised AI scientist, specifically in natural language understanding. He has contributed to major online tech magazines, and his piece titled Machine Learning Won't Solve Natural Language Understanding was a runner-up in the awards for most influential and viewed articles in The Gradient. His career has spanned significant industry positions at places such as the American Institutes for Research, AT&T Bell Labs, IBM Watson, and Cognos. In addition, he's held roles in academia at Carleton University, the New Jersey Institute of Technology, the University of Windsor, and the American University of Beirut. He is currently Senior Research Scientist at Northern Eastern University. So if you're watching this as the live stream now, please add your comments and your questions as Walid and John are talking. And at about the 30-minute mark, we'll start posting those questions to Walid and John for discussion. So thanks again for joining us. And John, I will hand over to you to take it from here.
Thank you, Beth. That's great. The challenge is to get my meeting plan showing. Where is that? Here it is. So at Pat, what we decided was that 2023 has to be the year for the theory of understanding. So we've got a lot of progress in AI that we've seen over the last few years, but the missing piece seems to be understanding as people do. So what better way of focusing on that than by making this the year of the theory of understanding? Today we're talking about what language models can never do because the relevant information is not in the data. Well, what does that mean? What we're going to do is introduce Walid Saba. I've seen a number of videos of people talking about the subject, and I think Walid's one of the best. So Walid, how about I hand over to you and you can continue.
All right, thanks. And I want to thank everybody that is joining us, and also thank Pat Inc., John, and Beth for inviting me. So I'm gonna spend some time saying my opinion on why large language models that have been the talk of the whole tech industry, actually, why they have a ceiling in what they can do. As impressive as the latest results have been, mostly on generative stuff, syntax and basic lexical semantics, I want to discuss why technically, by technically I mean in theory, this is not an opinion, why they cannot scale into full language understanding. Now, the word understanding, we use it all the time, somewhat informally. As far as language understanding, the word understanding and language understanding to me means a very simple thing, actually. So for me, language understanding happens when if I hear an utterance, I can create a mental picture or a mental model of how things should be if what I heard was correct. In a sense, that's what. So I understood John is driving a red convertible sports car if I can imagine how the word would be if that statement was correct. But generally speaking, this is what, to me, understanding is. You have a speaker and a listener, or a writer and a reader, and let's say A and B, and A is trying to convey a thought that they have. The thought is in what we call an I language, an internal language. Actually, Jerry Fodor calls it the language of thought. Some people call it mentalese, whatever that language is. It's an internal language. So I have a thought and I want to convey it to someone. I encode it in an E language, in an external language, English, German, Danish, whatever. And then the listener decodes that external utterance, and hopefully they get at the thought that A was trying to convey. So we say B understood A if the thought that B reconstructed is as close to the thought that A was trying to convey. That to me is understanding. So I understood someone if I can recover the thought they were trying to convey. Now, with that in mind, there are many technical, again, technical meaning theoretical reasons why large language models were not scaled to full language understanding. The most obvious one that, at least to me, is very important is that most of the what we call naive physics, basic knowledge of how the world around us runs, basic knowledge of time and space and causality, and all that information is not in the text. And for full language understanding, it is definitely needed. Here's an example. If I say John told his mother that he put his baseball glove in his bag, and then his mother replied that if that's the case, then your glove is already in the car. Implicit here is that John's bag is now in the car. And this understanding happens because, but large language models will fail miserably with this stuff. Implicitly, this understanding comes from the fact that if I put an object in a container and I put all that object again in another container, then the first object should be there too. That's a basic template, what I like to call universally valid cognitive templates. And there are so many of these. And none of it, and this is the key point, none of it is explicitly mentioned in text. We never speak of these things, we assume them. And so, basic reasoning here. This information is needed to understand text. This information is never in the text. Conclusion, large language models, no matter how much text they consume, they will never discover this information. So formally, this is the cognitive template. If I have two physical objects, X and Y isn't contained in X, then the location of X will always be the location of Y. The location of X will always be the location of, sorry, the location of Y will always be the location of X. Unless some exceptional thing happened, I don't want to get into that, you can override default behavior. So for example, if I put an ice cube in the car and I drove 5 hours, it's not going to stay there. So there are some exceptions, but we can also deal with those. The other big issue with large language models is that we don't, also in the text, we never explicitly state what all of us know. For communication effectiveness, I say the minimum I need to say to convey a thought and not more. I don't say stuff that I can safely assume any human being by the age of 4 or 5 knows. An example is the trophy did not, this is not the Winograd schema, although I'm using a similar example. The trophy did not fit in the gray suitcase because it was too big. And because of that, there was no point trying to put it in the blue suitcase. Now, obviously, and by the way, I used to do these experiments, and I did one on my kid years ago. I asked him to put the laptop in a small bag. It didn't fit. Then I asked him to put it in a smaller one. The reply was, Dad. So we know that if X is smaller than Y and Y is smaller than Z, then X is smaller than Z. And there are many relations like this that are transitive. Older than, bigger than, smaller than, heavier than, etc. So again, they do miserably here because they don't know this universally valid cognitive template that for X to fit in Y, first of all, it must be smaller, and it's an if and only if, and that smaller is transitive. Again, this information is never explicitly stated in the text, and as we can see, we need it to do full understanding. Another proof that there's a limit to what large language models can do. Like I said, there are a number of these universally valid cognitive templates. I can supply you with some of them. I'm actually doing a write-up on formalizing the most obvious ones. Okay, another big problem with their large language models, again, same theme, information that's not in the data and will never be explicitly stated in any text. Large language models might figure out something is possible or not, or even if it's probable or not. But they will never get at what is the most plausible, and that's what we need for understanding. Obviously, for something to be probable, it has to be possible, and then, but probable, not all probable things are as plausible. Some are more plausible than the others, and that's what we need in language understanding. So, for example, a teenager shot a policeman, and eyewitnesses said he managed to flee away trying to escape further injuries. What does he refer to? Both possibilities are probable, but not equally probable. One is more plausible than the other. This is a key point here. I hope people appreciate what I'm trying to say. Plausibility is never in the data. Plausibility is in the common sense world we live in. We don't discuss plausibility. What is more plausible? We assume we know what is more plausible. So yes, usually the shooter tries to flee. But here I'm explicitly saying that the policeman fled away to escape further injuries. So things like that, large language models will never get that. And I don't mean they're not there yet. In theory, this information is not in the text, so there's a never here. Similar example, but with a slight variation. Again, common sense knowledge of events is not in the text. We never explicitly state these things. So Dr. Smith told Dave that he should be done reading his thesis in 1 week. What does he refer to? Again, it gets this wrong. Yeah, both can be, both are a possibility, but we know that the student writing the thesis obviously read the thesis, so he should be done reading his thesis, not the student. Obviously, the student read the thesis. They are writing it. We're hoping that they read it. So obviously here, he should be done reading the thesis is Dr. Smith. And again, it's about plausibility, one event is more plausible than the other, although probability-wise, they're both probable. Another big reason why large language models will not scale to full understanding, this is more of a technical issue, but I'll show you a linguistic example. How does this translate to language? The idea here is deep neural networks are purely extensional models. They don't deal with structure semantics or intention with an S. The idea here is if I have a tensor like 14, you can think of another vector, but 14 is a tensor. It's a simple scalar tensor. It works the same way, it doesn't matter. 14, when I compose the inputs in some linear combination, even if I use a nonlinear activation function, doesn't matter. In the end, I have an output, say 14. Now, 14 could be the result of how many inputs? Infinite, actually. The point here is that in deep neural networks, you cannot decompose the composition. You lose the structural information. I'll show you why that is important soon, but that's the idea now. And I have in an article I wrote, I give an example. You have a ReLU function and a simple neuron with only 2 inputs. If you have an output 0.87, there's an infinite number of ways to get that. By the way, this is the reason why neural networks will always be susceptible to adversarial attacks, because I can always make you produce a desired output that I want from inputs that are wrong. So I can always force you to misclassify in a way. And it's related to intention, the logical notion of intention. Why is that important? I'll give a simple example here. So Paris is the largest city in France. Oops. ChatGPT says, yeah, indeed. Okay. So I then said, well, Mary said she would like to visit Paris. Does that mean Mary would like to visit the largest city in France, since Paris is the largest city in France? It says, yeah, if Mary said she would like to visit Paris, that means she would like to visit the largest city in France. And that's absolutely wrong. I'm giving a simple example, but the phenomena translates into deeper problems. So for ChatGPT, Paris and the largest city in France are the same. Well, that's not true, actually. As you can see, the inference that it's made is wrong. Mary would like to visit Paris, but Mary has no idea that she would like to visit the largest city in France. She doesn't even know, probably, that it's the largest city in France. The issue here is that Paris and the largest city in France are equal in one small sense only. They happen to, at some point in time, refer to the same object. But as objects of thought, these two are completely different. Intentionally, they are completely different. And in language, you get funny stuff if you don't realize that. And deep neural networks can never realize that. Like I said, because they are extensional models. And once you compose, you lost the structure, so you don't have any intentional knowledge. Okay, so I just went through 5 technical reasons. Technical / theoretical, again. In other words, these are not opinions I have. I can get into opinions, but these are not opinions. These are technical reasons why there's a ceiling to how far large language models can go. Each of them is very serious on its own, actually. Each of them is enough on its own to look elsewhere. To summarize them, most of the information we need is not in the text. You recall the contained in template, and we need it to understand language. Statistical information cannot approximate semantics. Sometimes 2 things are equally probable. And we need to decide which one is the most plausible, and plausibility is not in the text. Number 3, the stuff I just went through, intention and compositionality. And finally, number 4 is something I didn't get to here. But again, it's on its own, it's enough to say large language models will never scale to full NLU. And it's a technical mathematical proof that has been established that machine learning is essentially compression. But we know language understanding is about uncompressing and discovering what was not said. So technically, they contradict each other. I have this stuff summarized in this article, more or less, although I added a few things here. And that's my opinion on why large language models cannot ever scale to full language understanding.
Excellent, Walid. Thank you very much. So, unfortunately, I've got the challenge of following up from something that was nice and concise with a little bit of theory and a few other things on top of that. So let's see how we go. And we will get to the questions at the end. Sorry, Beth.
I was just going to say, and I'll keep you honest on time because we are accumulating questions, but I'm promising that we will get to them at in a suitable time so that we can have good discussion. Okay, great.
All right, well, let me get on with a little bit of theory then. So Walid's just shown us the some of the things that large language models can't do, but then the question is, what should a language model look like? And here I'm taking you to the Roland reference grammar model, and how Roland reference grammar works. It's a linguistic framework. It starts with the concept of syntax. It's technically morphosyntax, so it's the words plus the word sequences that then link across the world's languages to some semantic representation. And the idea is that that semantic representation is universal. And it does it in respect of context, so what you're currently discussing. So the great news is that you finish up with this multilinguality. So if you can convert from a language to an unambiguous representation, then in theory you can use this linking algorithm to generate back into any of the world's languages. And that's what Roland reference grammar has been demonstrating for the last 40 years or so. The obvious point is that what's not in the data? Well, this semantic representation is not in the data. When you compose the words in that particular language, you're putting together the elements that make that language work and that provide the appropriate meaning. And that's the whole point of having the coding system that way for the language, that it allows you to get to the correct semantic representation. The question about context is an important one, though, because what we understand comes from the current situation that we're dealing with. And this is an old example from Oliver's Selfridge. So that was Marvin Minsky's supervisor, I think. So we're going back to the 1950s. And there's this example here where the H and the A is exactly the same written character. So if you want to have a vision system that recognizes letters and then passes it on to a machine to recognize words, you've got a problem because this is both an H and an A. So if we use that same analogy, in terms of the semantics, this is te and also the, and this is chit and cat. And in context, there's a nice phrase in English, the cat, which you'll pick up on, so you'll say that's what it is. But we're always solving these problems in context. And I know what you're going to say, that this is good in theory, but does it work in practice? And yes, the good news is it does work in practice. So in 2017, we were in our office in Palo Alto, and we had a visiting expert in the education market, and he said, well, you've got this theory, but can you prove that it works? So what we did was we took the Facebook conversational task tests, and we did 9 of them just to prove that this system works. And what we found was, firstly, surprisingly, that some of the training data was incorrect. And we found it because we just tested it and we said, hang on, this doesn't make any sense. And so the training data, which is how machine learning starts, then was generating invalid test results. And so we were able to get 100% right by simply understanding both the training data and the results. An example of that would be Beth is at the park. She went to the kitchen. Where is Beth? And what the Facebook test would do is it would say kitchen, and what we would do is say in the kitchen, because kitchen isn't actually a location, it's a name of something. and that was the limit of the test at that point in time. The reason this is important, and I'm focusing on this one slide, is that when you're doing this linking, you want it to be right. So a test-driven system is the thing that's also missing from machine learning applications today. You can load up a whole lot of stuff, and whether or not you get the right result is going to be determined by actual use. What you want to do is like a calculator. If you have a million different operations you want to test all of them, and then you can release your product. And we can do exactly the same thing with an NLU system based on this type of logical model. So let's just go back 110 years. I like the history because there's been some really clever people that have actually set the framework for us. So Charles Sanders Peirce died in 1910, and he had this concept, and the concept of semiotics. There was another one done by de Saussure in Europe around the same time. They didn't work together, and I think the Peirce model is superior for the reason I'm going to show here. So the idea is that in language you've got these signs. So those are the words in the language, and those are indicating something. And as a child, you're learning that, egg links to some sort of object. So you've got your context, which are the real objects, and then you've got your signs, which are connecting to them. And what Peirce did was he put in this intermediate level, which is an interpretant. So if you see the word he in Walid's example, you've got a pronoun, which is what he called an index. So there's not a specific object you're referring to. There's the current object that you're referring to. You have to work out, if there's a number of choices, which one it is, but you have to work out that object. So he is always referring to something different in general. If it's a symbol, it's like egg, it's always referring to this class of things. So your signs can link either to indexes, which as luck would have it, are the majority of the words that we use. We use a lot more indexes than symbols to communicate. And that's one of the reasons distributional semantics, which is the idea that if you have a word vector, it's giving you a good indication of what's going on. That doesn't work for indexes because indexes refer to different things. And so last point is that this is introducing the concept of a dictionary and an encyclopedia, which were terms used a lot back in the 50s and 60s. So this sign here is like a word form. So if you go to a dictionary, you can look up your word and then you can have a look at your definition. So the different interpretations you get are coming from your dictionary definition. So if you make this language independent, which is what we've done, you then have the ability to have one meaning for the world's objects, and then you can generate a definition based on how it relates to other things. That's the dictionary. And then when you have a sentence which is combining these elements, now that's encyclopedic knowledge. So, Beth walked to the park. That concept is something that you can store in context, and that's what we did with the Facebook tests. So let's have a look at how language really works and expose some of the deficiencies of a large language model. So what's not in the data? If you said, was Steve Jobs a CEO, no cleaner? To me, that means the question was was Steve Jobs a cleaner? And the system comes back and says, yes, this is ChatGPT by OpenAI, so the current research version. Yes, Steve Jobs was the CEO, he co-founded Apple. So it's just ignored the no cleaner bit, which is what statistical systems often do. If you look at our launch example from 2016 in San Francisco, we've got call Beth, no Samantha, no John, no text. And that sequence of different meanings is, if you say call Beth, no Samantha, that means call Samantha. No John, that means call John. No text means text John. So when you say who is called, the system says, I don't know. Who is texted John, because that's what it meant. Was Beth called? I don't know, because we don't know who was called. And then here's our meaning breakdown. So it means you text John. We've got a representation there. It's a imperative, it's a command, so you is implied. And you can compare that to the ChatGPT example. So that's one example where the error correction's not in the data because you have to understand what was just said. So here's the ChatGPT architecture if you haven't seen it before. What we see here is that these red bits that I've highlighted in their workflow are where a person gets involved. So they get a prompt, a person gets involved to work out how to display that, what the desired output is, and then they pass it back to the pre-trained model, the GPT 3.5 in that case, to do some more learning. And then somebody else takes the output of the system in trial, and then they rank what the best answers are based on the outputs that have already been labeled by somebody else. And then you do some more training. So there's humans in the loop. And I think that's probably a bad model for AI. When this came out, there were a lot of people saying AGI has solved everything about the AI revolution is now only a year away. And the trouble is, if you've got people in the loop, I think it's going to be hard to justify that as being super intelligent machine, because you've got people that are programming it. The other point that I'd make is when you look at language, and not today, but when you look at some of the complex results of simple sentences, there's hundreds of elements that are all interacting. You need to have the word sense disambiguation, the tense, the modality, the aspect. All of that has to be tracked, and you've got to track it perfectly if you want to be able to use a lossless representation, as people do when we're interacting with each other. So the idea of putting people in the loop of that, if you've got hundreds of variables you've got to do perfectly, it's not going to work. And we'll see that it doesn't work in a couple of the examples that I'm going to show. And the last point that I'll make, and this came from somebody on LinkedIn, I haven't been able to validate the source of the information, but that labeling step is about 350 person years of work. Now, whether or not that was for ChatGPT or for all of the different systems, I'm not sure, but it sounds like there's a big amount of effort going on to that labeling exercise. Okay, so now we've got this system that's proposed as artificial general intelligence. Let's see how it does at something like a simple fact. So on the left-hand side there, you can see the General Magic example. So General Magic was a company in the 1990s. They were producing what was going to be like an iPhone back in those days, a phone plus organizer plus email. And they failed about 1994, although the company didn't wind up for another 10 years. But you can see here there's this guy, Tony Fadell, famous guy. He built the iPod at Apple after that, and then he was involved in the iPhone. So I'm going to ask a simple question. Did General Magic staff work at Apple after its failure? Because I've got this article, so I know yes. And it just says it's possible that some former employees may have gone to work at Apple. And General Magic was a technology company, so it tells me a bit about that. And you think, okay, well, so it doesn't know that story, but let's just ask another question. Did Tony Fadell work for Apple? Yes, he worked for Apple after General Magic. And as you read down here, it says, let's see, he was responsible for leading the development of the iPod. He was a key member of the team that developed the iPhone. So when I said, did General Magic staff work at Apple, it knew the answer, but it didn't have access to give that to me in its response. So what are the possible failures? Well, GPT might not know, but it's in this answer, so it does know. Did the person that did the labeling just not get the right distinctions? Probably, possibly. Is there some other reason? I would argue that the representation for that's not sufficient to do what a human would do, which is if you work at a company and you ask a question about a company, they're both synonymous to some degree. What else have we got? This is the famous example. Thomas Beaver is a guy from, I think this was 1970s. This example, the horse raced past, the barn fell. It's a garden path sentence. You can look it up at Thomas's website, Wikipedia. The horse raced past, the barn fell means the horse that raced past the barn fell. And by putting that in that garden path sentence, it says, I didn't understand it, and it quotes, who fell in the horse raced past the barn fell does not make sense. Well, that's true, because it's not picked the start and end of the sentence. So I helped it. I put in the quotes. Explain who fell in, quote, the horse raced past the barn fell. And it comes back and says, it's not clear who fell, blah, blah, blah. It is possible that the sentence is missing an important noun or verb. No, it's not. It's possible that you just haven't interpreted it correctly. And so that's the type of thing which is very common in language, where we bundle sentences inside other sentences. Sometimes it's ambiguous, sometimes it's garden path. We always seem to be able to work out language, and our machines should too. Okay, a more funny example. How are we going for time? I'm just about out of time. What should my wife be bought from a guy who doesn't like video editing? So what does that mean? Well, I'm just testing passive recognition. So a passive sentence is one where you don't have to specify the subject or the actor in that case. So somebody's going to buy my wife a present, and they're going to buy it from this guy who doesn't like video editing. And it suggests things that are obviously assuming that it's me buying my wife something, because it's suggesting jewelry, A spa day, that's okay. A cooking class, yeah, that's all right. A weekend getaway, yeah. A mini vacation can be a great way to spend quality time together and create lasting memories. Yeah, well, I'm sure my wife would enjoy that, but I'm not sure I want somebody else taking my wife to a weekend getaway. So, those are the types of challenges where, is that in the data? Well, it's actually unspecified who is buying the present, but that's a good list for me, not a good list for others. Last point is, what was it that we were trying to achieve with the great revolution from about 2012, the Chatbot Revolution, where we were going to make all systems work with human language? I'm putting this example into ChatGPT. So I don't work for Apple, I work on NLU. Is there an obvious role to help with future iPhones? Because obviously the better the NLU functionality is in an iPhone, the better the product's going to be. I mean, I think that was Steve Jobs' rationale behind Siri, etc. And it goes through an explanation about NLU and stuff, and then it says, without more information about John Ball's background, it's not possible to predict. Firstly, there is some stuff on the internet about me, and the only reason that they would be interested was because I work on NLU. So I've already given the premise that's enough for a human to give an answer. But there's this concept of goal-directed conversation, and that's what the revolution was about back in 2012, 2014, 2016. If you've got a system that's already doing a job, you've got your bank balance, you've got your orders from companies, you want to be able to help the user get their information and present it in language. That's what I think the whole concept is about. API.ai, now Dialogflow, was focused on how you can get access to that IT data. So here's the chatbot architecture, and this is my last slide. What people would do is they would work out what an intent was to get something like, what's the weather like in San Francisco? They would create the intent by writing hundreds of samples that would link with this distributional semantics concept, the word vectors, to that intent. And then based on what's said, you can have the developer write a webhook to call an API to the backend system and pull the information in. So there's your API, the green bit. And it was up to the developer to work out how to navigate the context to do more complicated examples of multiple intents to get to the right answer, which has some issues with it. So once the API is pulled back, then the developer can work out how to do the output data. So the point I'm making here is that if this is the holy grail of the next generation of systems where people are interacting with all the legacy IT systems, it's very important that that is possible. And if we look at this architecture here, I don't see how that's going to be solving the problem for us. ChatGPT has got a significant step to convert that into a developer type of application for goal-directed conversation. Okay, so now that I've used up most of our available time, maybe we can handle some questions. Okay, Mike. Powerful point of what's in the LLM and what this is for you, Walid, on what's in the LLM and what's not in the LLM. At a higher level, though, we can still use statistical approaches to get at common sense from non-LLM paths. So can we, Walid? Oh, and
Me.
sorry.
So that's for me.
Yes.
No, my answer would be no, and I think one of the examples shows that clearly. The problem with statistical approaches is, what if the probabilities are all equal, which is the case in many situations. Like I said, plausibility is not in the data, and plausibility has to do with common sense. Something is more plausible than the other. That's not in the data. Probabilities are, but knowing what's probable will not get me there, because there are things that are both probable, and worse yet, they are both probable and sometimes equally so. Like the trophy doesn't fit in the suitcase because it was too small. If I replace small by big, small and big statistically are equivalent. They co-occur in the same context with equal probability. So statistical approaches are not enough, because knowing what's probable is not enough, especially when probabilities are almost equal. I need something else. I need plausibility, which is not in the data.
All right, and as luck would have it, we have a follow-on question for you, Walid. We can use a different tech for different problems. LLMs aren't a universal tool for all problems, right?
That I agree with. I think, and there's a lot of talk now about hybrid AI. I think there's a misconception. Hybrid is not the answer. Modular AI is the answer. In other words, there are modules that are good at some task, like in software engineering. There are modules that will be coherent, small, coherent. They are specialized for one task. The challenge will then be in a large AI systems, how do these modules interact? But I agree, there's room for every one of these techniques.
Right, question from Connor. Also, dimensions are relevant. There could be a box that has a smaller volume than a larger box, but could fit the trophy because it's long and skinny.
Yeah, I mean, we're not trying to play visual games here. I mean, and I'm saying that with all sincerity. I mean, the cognitive templates cannot be disputed. We do have these universally valid cognitive.
Oh no, we've lost Walid. Oh dear. Well, what Walid was about to say was that we do have these cognitive templates, and they're universal. So the meaning representations are universal, and he's back. Let's.
Yeah, not sure.
I tried to cover for you, Walid, but.
Yeah. I mean,
I even jumped in. That now we're getting serious.
This is not about being, trying to be tricky or anything. These universally valid cognitive templates do exist. A 3-year-old starts to be aware of them without teaching them to anyone. For example, if an object goes out of sight, that doesn't mean it disappeared. It just means that it has been relocated somewhere else. We know of these things. It's another question, where do they come from and how do they get imprinted in our DNA? I don't know. The question is, obviously, they're not in the text, and these cannot be learned, by the way, because we're not allowed to learn them differently. Anything we're allowed to learn, we can learn differently. The universally valid cognitive templates are culture independent, age agnostic, culture agnostic, time and place agnostic. These are not things we learn from text. And I have ample proof that you need them to understand language.
Also, Walid, a couple of the comments that I noticed in the chat were around, well, what does that really mean? What does that sentence mean? And there's this concept of Grice's maxims that, he was either psychologist or philosopher. And he pointed out that when people say things, they're saying things in a really efficient way. And they're not lying, they're not trying to deceive. So if something didn't fit into the bag because it was too small, it could have been too small because of dimensions or whatever, but dimensions still means too small. So the actual sentence is still valid.
We're not trying to fool people when we communicate. And actually, the whole purpose of communicating is I'm trying to sincerely convey a thought. I want you to understand it. So, and there's been a lot of research in evolutionary linguistics that, like Grice said, for effective communication, we leave a lot of stuff out that I can safely assume you know. That stuff is not in the text, and no matter how much text we ingest, we're not going to find it in the text.
Language is an arbitrarily agreed upon system of communication. Words have no meaning or purpose other than what users of a language agree upon. NLU must accommodate this quantum reality.
You want to take it?
Yes. So it is the quantum reality. I'm not sure if that's referring to quantum theory or not, but certainly the idea of the arbitrariness of the words and morphology that we use is basically whatever the brain can do for that language to do the communications. Agreed.
My quick comment is the string itself has no meaning, but once we agree on the token, then it does have a meaning. In other words, BIRD, bird, as a string has no meaning, but once we agreed what it means, it now has a meaning and a rich meaning. It points to a class of animals that have feathers and a beak, and so uh, we do give meanings to words. It's that's semiotics. We have a token, and we use it to refer to concepts, to rich concepts. So in the end, words do have meanings, and even function words, by the way, which are completely ignored in large language models. But that's another discussion. Function words actually are the words that do determine the final meaning in the end. They are more crucial than content words in a way.
Right. Question from Mike Ma. For knowledge, appears to be two intuitive neurosymbolic approaches, including one, embed info from a graph into transformer. Two, augment graph with transformer. Does one make more sense? Alternate approach entirely. Embedding info from graph into transformer, I think, is the first model there.
Well, and my reply would be the third, the last option.
An alternate approach entirely.
Yeah, I am really large language models will do well in picking up low hanging fruits, doing text processing stuff, summarization, extraction of key topics, limited Q&A, but for full language understanding, the holy grail. If I have enough time, I'll go through the 5 technical reasons, mathematical reasons, theoretical reasons why these models will not scale. Intention alone is enough. These models are purely extensional. They're numeric. They don't keep the structure of the input. They lose it once you compose vectors. There are so many technical reasons. Actually, and my arguments are not entirely new. Jerry Fodor has these arguments laid out since 1988, and his attack has never been seriously answered. So I'm not saying something entirely new. Some of it is new, but not entirely.
Yeah, one of the things that I think we should be working on is lossless representation of knowledge. So, I called it the super knowledge graph, where you're taking language and converting it into a language independent representation that's exactly what was said in the first place. So you obviously have to resolve the context as in order to get that knowledge representation. But I think that's what our goal should be. And one of the reasons why 2023 is the year for the theory of understanding is we want to explore that in more detail and see, are there any reasons we can't get to it? Because ultimately, science should be telling us what we need to do. And if the latest theory doesn't account for it, well, let's work out what the right theory should be to get there. And Walid, with your expertise, it's one of those things we've got a great opportunity to do as we go forward this year.
Yeah, I hope so. I mean, the first battle is to actually make the whole discussion more sane and more scientific without high emotions. I mean, this is science, for God's sake. I mean, this is science, and when you have a proof that here's a model that cannot mathematically is a big word. It cannot, thou shalt not. It cannot model X and Y. I'm amazed sometimes by the replies I get, but what if we just said it cannot mathematically? So I think we should stop being emotional and maybe stop being too persuaded by media hype. This is a scientific argument, for God's sake. Autonomous driving costs us $200 billion, probably. I don't know the exact number, but billions. And I remember 3 years back when I was in the Valley, and I was telling them the best this can do is advanced cruise control. People would laugh at me because everything was deep, everything was big, deep learning, big
Right.
data, and they wouldn't listen. Do we want to do the same thing in language? I mean, are we chasing infinity now? What's next? 10 trillion parameters? There are things that are scientifically proven. Okay, so I think the discussion should be more sane, less emotional.
Regarding that last question, which was about can we use LLMs to acquire common knowledge from text sources and translate them into a symbolic model? If you think of it, that's what it looks like people do when you're learning a language. So a child is connecting up these meaningless sounds to the things that they're experiencing. And the challenge of just doing that from text is that there is no experience to combine that with. So if I say egg, 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 and there's an egg in front of me and I'm eating it, you're getting a knowledge of how to manipulate that object. But with text only or sound only, I don't see how you can do that. So can you create something? Yeah, but can it be human-like? I don't think so.
This is an excellent question. I keep I'm asked this question a lot, but I went through some examples where the information relevant is not in the text. So how do I get something that's not there? The reason common sense knowledge is not in the text, that's why we have effective communication. We don't say what we all know. We don't say what we don't need to say. That's the dilemma in language understanding. That's why it's difficult for machines. We communicate very effectively because I can leave out what I can safely assume you know. And so that stuff is not in the text. We don't actually say it. Okay. One example I gave is the containment relationship. This is one argument. The other one is, if we want to learn it from text, imagine a child want to discover all these things on their own. They'll be 40 years old before they can resolve the reference it. This is cognitively implausible, psychologically implausible, and computationally implausible. But the bigger problem is that this stuff is not in the text. We don't say it.
I think that's a great place to possibly wrap up, John and Walid, with discussion from Walid and John about why it's not about scale, because it's not in the data, what's not in the data, and limitations of large language models, as good and powerful as they are for certain things. How do we get to understanding? And as John said at the beginning of the call or the session, that 2023 must be about understanding human language. We have to get there, not just focus on generation. And Wally did allude to opportunity cost when he was talking about how much money has been sunk into autonomous vehicles. So the benefits and opportunities here are enormous for society, but there's an opportunity cost if we don't get this right, and we can. My parting words would be, and then I'll hand back to you, John and Wally, to say very final words. We will organise another session to cover what is the path forward. How do we make machines understand us? And so watch out for the plans for that, and I hope you can join us for the next session. John, Walid, final comments?
Actually, Walid, if you go first, because I want to leave the program with just a snippet of what I want to talk about in the next one.
Okay. First of all, thanks to everybody. Great questions. Thanks again, John and Beth. It's one thing to say why this approach cannot take us there, and it's another thing to suggest something, not only nag. We just didn't have time. There was no way to cover what I think is the right way, and it's stuff I've been working on for over 2 decades. So I'll have something to say about that in another session if we can have one.
You're just showing off because you're so young.
Jim has tried to sneak another. Jim has tried to sneak another question in. I wonder, though, if we follow up some of these questions in comments for the recording and in LinkedIn and YouTube.
Yeah, I'll go over them, and if something was coming my way, I'll be more than glad to answer it. Sure.
Great. Thanks, Walid. All right, well, I might finish up then by just taking you through what the system looks like that it is using the model that I mentioned, and I'd like to talk about this more in a future example. So if we take a look at how language works, let's just take an example like by. There's a massive amount of variety in language, so here's a bunch of ways of using the word by in questions and so forth. If we take this one and we just look at what the breakdown is, this is why I'm saying you don't want people doing this manually as a labeler or something. It is the man that bought the car from the dealer for $1 for Beth. When we look at the meaning of that, the second sentence in there, we've got the man's doing something. The man has the car and the dealer doesn't have the car, and the dealer has $1 and the man doesn't have $1. So that's the exchange process that's taking place. And if I take that and put it into conversation, this is where we just want 100% accuracy from the system to interact with us and generalize. Because ultimately generalization's the key. So now that I've got that sentence, we've got somebody buying. If we said, who sold the car? So selling is not in our training data, but that's the only training data we've got, the first sentence, who sold the car. And you could ask that in a bunch of ways. Who sold cars? Never do live typing. Never do live typing. The dealer did. So you can ask a bunch of questions. You can generalize like who sold artifacts. Artifacts. Right. So a car is a type of artifact if you happen to have that in your lexicon. Who sold it? We can use pronouns. So we're generalizing a lot. We're getting the same answer. But the point is that this isn't the first sentence that you would think of to say when you're describing somebody buying a car. And then you can use a completely different type of predicate that has a focus on something else. Who paid for the car? One error per sentence. The man did. So if the man bought it, so he's the one that paid for it. That would be our explanation. But you can also look at the other side of the exchange. Who paid $1? The man did. And let me just copy one other example, which was it Beth that he bought it for? Yes, it was. So that, yes, it was. We're referring to the whole concept there. There's no magic going on under the covers. We're tracking that main sentence that's embedded, and we're tracking the whole sentence. And as we saw before, that's the representation of the meaning of that. So I'd like to see us get to this being the fully tested version that anybody in the world can access for their language, where they're getting the particular meaning that they can use for applications. Because once you start coding from this, you've simplified the work of development significantly, and we've got a then virtuous circle to keep developing this. So let me just drop that off. So on that point, I'd say I think it's been a great start to the year. 2023 is looking very positive. It's a good year for understanding, and it's a good year for understanding how we understand. And on that note, I think we'll say goodbye. Look forward to answering your questions, and we'll see you next time.
Bye, everyone.